Hi, I'm Meta Spencer, and it's great to be back with my old friends. It feels like we're all old friends because we've done shows and forums together several times already about a particular project that the Canadian Potash Group is investigating, and that is the possibility of chilling Hudson Bay, possibly even refreezing it so to stay warm in the summer if we could. I say frozen in the summer. So there are various possibilities for attempting such a thing. And we've been investing one already. The Stephen Salter's favorite project, marine cloud brightening, which would
Which is
be
due to John Latham, not me. I'm just the engineer. John Latham, okay, and Sean Toomey are the people who
You always give credit to them, and that's very honorable of you. But the face I see repeatedly is Stephen Salter, so it's always great that you're here. And the idea there is that we would spray seawater, which would somehow, in a very long chain of events, whiten the clouds and therefore reflect more light back into space and save a little bit of the cooling underneath the clouds. So that's the approach that we started with, but we found there's a possibility that it might not cool it enough, especially since the Hudson Bay is already pretty warm, and can we refreeze it? I don't know. It's all going to be a big experiment to see. But there are other ways of doing things, so maybe we could combine two or three of the other options, and with using them all, have quite a significant impact on the temperature of the water and the ice. So that's the thing I want to explore a little bit today. And so I'm bringing in other friends who've already talked separately about their proposals, which would be, I guess, ocean iron fertilization. That was the original idea, but there are a number of variants on that idea today. So I don't think that term works. In fact, I hope you guys will come up with a snappier title than that silly acronym OIF, because I myself have to keep looking it up and finding out what exactly that stands for. And it's very off-putting. We need a good brand for your proposal. So think about something really catchy. So I'm going to introduce, I've already said hello to Stephen Salter, but the three fellows who are most engaged with this, the spin-offs of the ocean iron fertilization idea are Franz Weste, who's in Germany. He's a chemical engineer. Clive Ellsworth, who's a computer software professional in London, but he is very much involved with climate change issues and founded the Citizens Climate Lobby in UK. And Peter Fikowski, who's an engineer and philanthropist and all-around good guy. He is the author of Climate Restoration, which is my favorite book of the year, if not the decade. And if you have it, hold it up again, Peter, if you have it at hand. I want everybody to read this book. There you go. That's beautiful.
Climate restoration, the only future that will sustain the human race.
Exactly.
It'll make you smile and make your children smile.
That's wonderful. All right, let's get started. And I think you're a good one to kick off because I think you really are good at explaining this whole set of, here comes Adele Buckley, bless her heart. It's good to have a quick wash among us. And please explain this, all of the variants of this notion of ocean iron fertilization and how we might apply it in Hudson Bay, if at all possible.
Welcome to everyone who's listening. To get the terminology straight here, overall, we're looking at climate restoration, which is restoring the climate to levels that humans have actually survived. And so without getting very scientific, we just know that as parents, we want to get the climate back to something that we're humans have survived, and we're confident our grandchildren will survive. So that's the overall goal. Then getting the CO2 levels back down is a separate issue that we're not discussing today. And the ocean iron fertilization you referred to is the method that nature uses before ice ages. So we know that it works. Nature's done it 10 times. We know how nature does it. And the only reason we're not doing it is climate restoration isn't yet on the table, right? The UN back in 1990 said we have to stabilize greenhouse gas levels. And it didn't occur to them 32 years ago that we would actually have to restore them first. And so because it's not on the table, it's not being funded and not being done. And that's a different story for a different week.
Okay, can you give us a capsule? Because this thing has had so many iterations. You start off with the idea of spraying iron particles or finding dust being blown across the Atlantic from Africa to Brazil,
Yes.
and all of the chemical effects that go with that.
Yes.
And then there are many implications where you start using it in different contexts and different kinds of aerosols instead of iron. And I'm particularly interested in, why don't you explain the basic idea and then how it would have to be changed to be appropriate for an Arctic environment that's white?
Yes. Okay, good. So as I said, first we want to restore the climate. Second is we know how to do it. We know how nature does it. It's not difficult. We just need to change the context. And now we get down into the nitty-gritty of what do we need to do. And the two critical things, which has the Clive and Stephen and Franz and me here, is there's the cooling the planet, actually reflecting more sunlight out, which doesn't affect the chemistry at all, but does cool the planet. Then there's also methane removal. And methane is really important for two very important reasons. One is even though it's a very potent greenhouse gas. It produces about a half or a third of the warming on our planet right now. So if we can oxidize it, if we can reduce the level by half, then we can almost end global warming just from that cooling. Mm-hmm. And that seems to be eminently doable. That's really thanks to Franz and the work that he's done, and along with colleagues, including Clive. Mm-hmm. So that's the using methane to cool. The other thing that's critical about methane is our planet, of course, is warming, and the polar ice cap is being lost. We've lost 85% of the Arctic sea ice in the last 40 years or so, and 80%, and we're headed straight to zero sea ice in the summer in 2040. Whether it's 2030 or 2045, we don't know, but probably 2040. So the last time that happened was 50 million years ago, and there was a big burst of methane that came out of the melting permafrost under the Arctic Ocean. And most scientists figure that it's not likely. It is probably less than 1% chance that that'll happen a second time. On the other hand, there's a lot we don't know. And we do know that the last two times that our Earth lost the polar ice cap, we did get a big methane burst and huge extinction events. So it makes a lot of sense to protect ourselves and be able to oxidize that methane before we go extinct.
I know that we have two different approaches to cooling Hudson Bay. And we've already explored marine cloud brightening a number of times. We've also talked about the possibility of using iron to oxidize methane, and that would reduce global warming.
Yeah.
And also do things like feed the phytoplankton, which would have an additional benefit, and also create gases that would whiten the clouds. So some of these things have triple purpose functions. But the problem is you can't do all of these things in the Arctic because you don't want to ruin your albedo effect. And if Clive will explain what you folks are working on in your secret lab to find up with to find an alternative to iron and why that is necessary, I think we will be able to begin making our comparisons.
Okay. Well, let's just say that iron salt aerosol is ferric chloride is what we're talking about, iron 3 chloride.
Mhm.
And this is produced naturally from the iron content of mineral particles. So mineral particles, they tend to be oxides, iron oxide. And over the ocean, when you have phytoplankton in the ocean, they give off the smell of the sea. It's called dimethyl sulfide. It actually oxidizes in the air to produce sulfuric acid aerosols. Sounds scary, but that's the natural world. And these are the particles that nucleate clouds. Most of the clouds are over the ocean. But sulfuric acid aerosol reacts with sea salt to produce, let's say hydrogen chloride, produces sodium sulfite and hydrogen chloride. Now, HCl gas, hydrogen chloride gas, reacts with the iron oxide to make iron 3 chloride. Now, the thing about iron 3 chloride is it's photosensitive, and it responds to a photon by giving off a chlorine atom. So you get a lot of chlorine atoms coming from iron 3 chloride in the presence of sunshine. Now, the main thing that removes methane from the air, thing is methane we know it doesn't spontaneously combust. If you use it in your gas stove, you have to light it, don't you? So then when it's very diffuse in the air, it doesn't just combust. It needs a chemical radical to kind of hit it and oxidize it. Mostly how this happens is with the hydroxyl radical, OH radicals, and these are produced naturally in the troposphere, again, from the action of sunlight. But the interesting thing about chlorine atoms, chlorine, we normally think of it as a chlorine molecule, Cl2, but a chlorine atom on its own is much more reactive than a chlorine molecule. And it's reactive enough to oxidize methane molecule in the same kind of way that OH radicals do. It's just that it does it 16 times faster in dry air, and in very humid air, OH radicals tend to get absorbed into sort of water droplets, and they get taken away by the humidity, but the chlorine carries on. So it can be as much as 250 times more effective at oxidizing, removing methane from the atmosphere as OH radicals or the hydroxyl radical. So that's why we think it's pretty compelling. This is a natural process, and it's been proven, in laboratories in Germany in 2014 and 15. It's nicely written up by the researchers at the time, and we've been, promoting it ever since. And people are getting more open to it these days. It's fantastic. Yeah.
You have something spray this stuff in the air where you think there's methane, and it knocks out the methane, turns it into water and CO2.
Yeah, I mean, methane spreads throughout the atmosphere. It's it's there throughout the atmosphere, and iron 3 chloride can be made into a vapor. It can be we call it sublimating. It goes directly from solid to gas, to a vapor, a gas. So it's not really sprayed, but it's anyway. It is dispersed into the air. Yeah.
My understanding is that that's not what you want to do over Hudson Bay.
I don't know what the proposal is for Hudson Bay as regards iron salt aerosol. Maybe Franz, do you know about that?
Yes, everywhere where some ice surfaces or snow surfaces are, iron colors them. For instance, Greenland and in the Arctic region, we would not propose to use iron because it colors, and each coloring makes a reduction of the albedo.
Mhm.
and
It falls on the snow and the ice, and then the snow and the ice don't reflect the way they should because they're darker. So
yes,
what do you propose to do instead?
we take a similar reacting alternative to iron, which is pure white, and that's titanium,
Mhm,
titanium oxide.
mhm. And have you experimented with this, and do you know that it would work? Does it work pretty much the same way that the iron salt does, or does it, I mean, in that it would knock out the methane?
It's well known in the scientific community that titanium dioxide is a similar photosensitive like iron, and it produces OH radicals instead of chlorine atoms. But these OH radicals, they produce in the adjacent chlorides also chlorine atoms, and therefore it acts like iron.
Mhm. Okay, so it would have the same effect.
It would
Theoretically,
have the
in
same
theory.
effect, but don't color the ice.
Yeah, okay. That's what I was fishing for, because I'd heard your story before. Now, I think you also, in the last time we talked, you mentioned something that's a new angle on this, and I don't really understand how it relates to the other work that you've been doing on the iron salt and now the titanium spraying. But you mentioned something about black carbon, and
Yes,
your experiments with how to prevent black carbon from migrating to the Arctic and falling on the ice and ruining the albedo effect by absorbing light instead of reflecting it.
you know, black carbon takes up all sunlight which is shining on it,
Mhm.
and transforms it to heat. So it can be 50 degrees Celsius warmer than its environment. Hence, it makes the adjacent environment warmer, and it gives an updrift, which brings the black carbon high into the atmosphere until the stratosphere. And it is well known that black carbon takes up especially all kinds of chlorine in the which exist in the environment. For instance, the organic chlorines, the chloromethanes, bromomethanes, and iodomethanes, they absorb on the black carbon, and also all other even inorganic kinds of them, and they go up into the stratosphere. And it is well known that the halogens, the chlorines and iodines and bromines and so on, that they destroy the ozone layer there.
Mhm.
So the black carbons act as a shuttle of these substances. They shuttle them into the stratosphere, and there they destroy the ozone hole.
Okay,
And
now how
as
would your proposal? I don't see the connection. How this thing about spraying iron or titanium? How is that going to affect black carbon?
So let me put the cycle to an end, and then I will.
Yeah, sure. Finish. I interrupted you. Sorry.
So, you know, in the stratosphere and between stratosphere and equator, there is the so-called Brewer-Dobson
Circulation.
circulation of the air, and these black carbon, which is going into the stratosphere, or gets down in the into this Brewer-Dobson circle, and this air from the Brewer-Dobson circle comes down in the Arctic. Now we come to the problem of the Hudson Bay and Greenland and so on.
Mhm.
And in the Arctic, you find, especially in winter time, a dense haze of black carbon and soot and so on particles in the air, and this goes onto the surfaces
I've seen pictures
and
of
color the
of
surface.
the ice that's practically black. Yeah,
Hmm.
so I imagine large areas are
Yeah.
really affected. Mhm.
Yes, and that's a great problem. The Arctic heats much faster than the globe in average,
Mhm.
3 or 4 times faster. So, how can we stop this? And
Mhm.
we can do it by a similar process. When we use our iron 3 chloride or a titanium process, we color also the carbon particles. They get a wider yellow color instead of a black color.
While
So
they're
they
in
can't,
while they're in the stratosphere.
and so they can't get up
Before they get to the stratosphere,
before
in the troposphere, where it's
in the troposphere.
dispersed. Yeah.
Oh, oh.
And
You're going to go up there with a paintbrush and paint all those black carbon things before they can do any damage.
Yes.
Fortunately, they paint themselves. This is
And-
tiny particles that oxidize.
Okay, now you're
it's
painting
chem-
them with what? You're when you send this titanium up there, that's what's going to do the job for us. It's going to recolor the black carbon.
These black carbon, it comes from any combustion processes,
Yeah.
from ship engines or from
Bushfires.
wildfires. Yeah.
bushfires. We cannot. We should put it on the bushfires, but in stacks of power stations or ships or any other kind of technical combustion processes, we can use our process of producing these isoaerosol or TOA aerosol, which we call
TOA is titanium. Is that it?
Yes.
And you, in other words, you're going to try to mix these things while they're around us, and then they're going to be colored before they even get to the stratosphere. And
Yes.
when they
You don't really
fall,
want to
they'll
mix
be
them around
lighter.
people.
And you really don't need much of them. You need only to color the surface, and these compounds we use touch to the carbon surface. That's
Okay,
well
now
known.
this is going to be a separate operation, though. When you actually go out and start doing the work, these are 2 different processes. One of them is you're going to go up to I'm imagining now, let's see. You're going to go up to Hudson Bay and you spray titanium around in the air, and that's going to knock out the methane. But the other process is you're going to go around to factories that are emitting various kinds of carbon, and you tell them to spray a little of that stuff as your stuff comes out into the atmosphere, and that'll handle it that way. Is that right? You've got two different, in terms of logistics of how you're going to do the work. You've got two
Yes,
different projects.
we can do it. We can do it in two ways, but the result is the same.
Excuse me, Franz, I need to go in a minute. Let me just ask a quick question.
Yeah.
Have you calculated how much titanium would be required to per year to keep our glaciers white?
We are. If I think of the black carbon, we are in the beginning of our. We are writing a paper, and there we can give more details. In the moment, without Clive, I cannot say anything.
Right. Right.
Yeah.
And we are calculating now.
It's not
It's a very
huge
fresh-
amounts. Yeah.
It's a very fresh idea.
Do you have any estimate, like per square meter? Is it like a gram per square meter, or a milligram?
I think we only need to color the black carbon particles when they come off the stack. Then we don't need to use much, very, very low dosage.
Yeah. And the reason is because it operates in a photocatalytic cycle. Does this work in a cycle as well, Franz? Where
Yes,
it just goes round and round and
Yes.
round, using the titanium as a catalyst,
Yes.
but driven by sunshine.
But it will not. This which you give on the black carbon, it doesn't come down in the
I see.
Arctic because the black carbon cannot act as a shuttle
Right.
Yeah.
any
Okay.
longer.
Doesn't go into the
Thanks.
stratosphere.
Yeah.
And I
Presumably
need to
gets
go,
rained out
so-
more easily as well,
Thank you.
Franz. Yeah. Okay. Thank you.
I have read that the International Marine Organization has got an agreement with ship owners to either reduce or eliminate black carbon. So how does this fit into the picture?
They use scrubbers to reduce SO2 emissions and also the black carbon emissions, but these processes are not totally complete. 10 or 20% will always leave the stack, the flue stack.
But wouldn't that be sufficient to have a very beneficial effect if only 10 or 20% of current emissions are remaining?
If you can stop its upflowing in the atmosphere, it's very effective.
Well, it would be cheaper than trying to get it after it gets to the atmosphere.
But we want also to get the methane depleted, so we should use the amount that methane is reduced in an appropriate way.
So now, when you even you're out over the ocean someplace, and there's a ship emitting black carbon, and you want them to capture it and not let so much out, but whatever gets out, you're going to dose it with some of your titanium, and that's going to it's going to have both effects. Is that right? It's going to lighten the color of the black carbon, and whatever methane is around, it's going to convert it into water and CO2. So it has a dual purpose. Is that right?
Multi-purpose. Removal of black carbon, removal of methane. In humid air, it makes clouds like any aerosol particles. So that has a cooling effect as well.
And the black carbon becomes oxidized by this process and becomes also to cloud condensation nuclei.
Yeah.
Okay,
So, but the thing
well,
is, we're talking about a natural, enhancing a natural process. So this is going on all throughout the atmosphere anyway.
you mean there's
and-
titanium out there doing that already?
Not so much titanium. There's a little bit of titanium in mineral dust. Mainly
Very
iron,
little
I think.
bit.
Yeah.
Very little bit.
A very little bit, yeah. So, but it's the process of oxidation. We generalize it as this is an oxidative process. Without the troposphere being oxidative, there'd be all kinds of, pollution still in the air. I mean, removes pollution from the air. So we're mimicking, enhancing this natural process that cleans the air anyway. In the case of ship smokestacks, if they're going to remove all the pollution themselves, well, great. But we think it's a platform that moves across the ocean through remote areas of ocean where most of the air is, most of the world is, and it's it's an ideal place to disperse this stuff if it's allowed, if it's obviously proven to be safe, which we think it will be, because it's mimicking a natural process and enhancing that process that removes methane anyway. So we're talking about strengthening the methane sink, strengthening this sink that removes black carbon from the air, hopefully fast enough so that hardly any of it goes up to the stratosphere and doesn't take up these halogenated compounds up to the stratosphere, doesn't come down in the Arctic, doesn't stop the heat coming out during the winter because you've got all this black haze hanging over it during the winter, doesn't discolor the ice. This is what we're proposing.
Well, it sounds beautiful. It sounds also very expensive. Imagine.
Doesn't have to be. No, I mean, ships are going across the sea anyway, and it's a very small amount. Sorry?
Titanium is not, I assume, not cheap.
Well, titanium for the Arctic, but for most of the non-polar world, you don't need titanium.
Salt.
Iron salts will do it.
Sure. Okay. Got it. Okay. Well, I think now we're going to leave aside the business of iron salt over the ocean and focus just on the titanium in the Arctic, because not to denigrate anything, because this is a wonderful project, clearly, but I want to see how it would fit together with Stephen's proposal of marine cloud brightening over Hudson Bay. Now, we have pretty clear plans. We have an idea that we're going to set up about 4 stations along the shore of the Hudson Bay, and we're going to have a wind turbine that will provide the energy and stuff. And whenever the satellites tell us that there's a good looking cloud coming along that could use a little whitening, we have a special nozzle that Stephen is building or will build, and it's going to spray seawater up there, and we're going to have a brighter cloud, and that's going to help cool the Hudson Bay. But that may not be enough to do it, and it's going to take a while anyway because he doesn't have his nozzles ready. So it'll be several years before we have these nozzles. In the meantime, I believe you folks are almost ready. You could start this summer if somebody would give you the money and the government would say okay. You could start spraying titanium over Hudson Bay or the region and knock out some of the methane that's coming out of that the wetlands on the South Shore, which I think is a very one of the largest sources of wetlands in the world. And now, Stephen, I want you to. I've been keeping you quiet while they expound on their theories, but why don't you talk about your vision of how these two operations may or may not fit together?
Right. Well, first of all, I want to emphasize the dangers of methane. It really is a very nasty greenhouse gas. In the first year that it's released, it's about 200 times worse than CO2. It's sort of 28 times worse if you average it over 100 years. But in the short term, it's It's very, very bad indeed. And the trouble is it's going to be released if you have any warming up of the permafrost or the seabed under the Arctic. There's an enormous amounts of methane that have stuck now in things called clathrates. If the temperature is below a certain amount and the pressure is above a certain amount, they're stuck down on the seabed, but they could easily come out. And there's evidence that they are already. You can see it bubbling it up. And occasionally in Siberia, there's a great big explosion where the methane has been collecting underground and gets released. Now, a thing I'd like to ask the chemists here, I can make chlorine at sea. I'm trying to use technologies that don't need large amounts of materials being moved around, but I could make chlorine at sea, and I could release ordinary chlorine gas, and I'd like to know if that would help with the methane. I'll be doing some chlorine anyway because it's a good way to sterilize the water that I want to spray, and I don't want bugs growing in the water, so I'm stripping all the oxygen out of it, and I'm stripping all the carbon dioxide out of it, which I can do just by putting it into a vacuum. But I can also make chlorine, Cl2, with electrolysis, electrolyzing salt. So would that be useful for getting rid of methane if I can produce some chlorine?
Yes, sure. There exists a process of Matthew Johnson from the University of Copenhagen.
Mm-hmm.
They use chlorine for this purpose. You can also
can you tell me how much they need?
depleting.
Can you tell me how much chlorine is needed? How many atoms of methane does one atom of chlorine?
Only one to one.
1 to 1.
Yeah.
Now that means rather a lot of chlorine then.
It does.
Hmm.
It does. But because it's not doesn't operate in a cycle, that it's used and then it's gone. It goes as HCl. But it's highly compatible with iron salt aerosol, because iron salt aerosol needs HCl to be gas to be in the air, because it'll then recycle it, keep it going round and knocking out more and more.
So it would be a good thing to do on its own if you're doing the titanium.
And if you sterilize the water, it's a very good byproduct.
Yeah.
Mm. Yeah.
Okay. Well, I might have to have a bit more power going into the chlorination, right? Well, okay. So we really do need to worry about methane as well as heat on its own, and the experiment that I'd like to do is to take photographs of cloud patterns from a satellite and to rotate them so that the wind directions at the level of where we're going to be operate are all aligned. And then I wouldn't expect to be able to see a brightness of a cloud, because I need to see a brightness change of about 15% to be able to detect one grey bar from another grey bar. But I wouldn't be able to detect the amount of contrast change in the cloud that we need to save civilization. But what I could do is to take a large number, maybe 100 satellite images, do the rotations, and then add all the numbers up. And this allows the contrast to be enhanced. And I've got a computer modeling of this, and I can show you the results of it. And this allows you to pick up a very, very faint change of contrast, which is enough for what we need to solve the temperature problem. And provided I can know which direction the wind's blowing, and I can align the images in the computer, then I'll be able to detect a very small release of the amount of salt we're putting up. And this might be able to convince people who understand it that it's going to work. I don't want to have anybody else doing other experiments in the same place at the same time, but because we won't be able to tell who's to blame or who's to get the credit. But I'm sure that we would be able to either be far enough apart from one another or different in months. You know, you could have May and I'll have June, and you can have July and I'll have August. So that's the kind of way we need to do it. I think the Hudson Bay is big enough for everybody to have a go and keep it private. So let's assume that's going to happen. There will be infrastructure and offices and energy supplies and food and transport and stuff that could be common to both experiments.
Mhm. I'm just wondering, is there a special time of year? Because I guess you need light also, don't you? You need.
Yes. I want to do it in May, June, July, really.
Yes.
April, May to August, perhaps. But
Yeah, it wouldn't work.
you can get rid of methane. There'll also be more methane in the warmer time of the year, because if it's coming up from the seabed, then that'll be coming up in the warm time, which probably would be a bit later in the year. It might be summer to autumn rather than spring to summer.
Mm-hmm. Okay, now my impression is that both of you need sunlight in order to have your experiment work, right? I know that iron salt requires light, but I presume that the titanium chemical reaction also is triggered by light, and therefore you don't do it in the winter when it's dark in the Arctic. So both of you want to work in the Hudson Bay in the summertime. Now, is it possible? You know, Hudson Bay is a huge thing. It's just enormous. And I'm just not sure, but whether or not you could you could take clouds that are in different locations and experiment at the same time.
I'm sure we could, yeah. I looked at the map and it is big. I'm sure we could both be there in different bits of it.
Okay. So it is possible that if we were to set up one of the things that Peter Wadhams was keen on was maybe having a research base in Churchill, Manitoba, where there's a wonderful new marine laboratory. And it would be a good place to have the headquarters of the operation, and both of these things could be done there, with maybe a common set of staff people, whatever is needed to run this thing. I have no idea what the administration of a project of this kind would look like. I know that Stephen, you estimated that including the cost of developing the nozzle, that you think your experiment could be done for about $30 million. And I'm wondering if how quickly, Franz, how quickly you think you could put together if somebody gave you all the money you need, how soon could you start doing this, and how much money would it take to do an experiment? How long would it take? What would this whole project look like from your point of view?
We have to ask the person who is responsible on the other side, who has the money, how fast, and if he would help, and so on. Because we need some we cannot do it, I think, in a 2 or 3 months, or in this summer. Impossible. We need a longer time to prepare all the things we need.
Yeah.
Okay.
Yeah. So we have a partner. It's kind of getting started, and we've been sort of in the wilderness for so long. And if money and regulatory authority comes along and says, we need you to do this, we need to test it, and then when it's we need to see it's working, and we need to make some guidelines and do the field trials as fast as you can. If the money's there, fantastic, we'll go for it. Up to now, it's been, can you do another paper? Can you do another paper? Oh, we're not sure about this. It does that, and it does so many things. We can't get our head around all this. But people are now coming around to it, that a natural process tend to do lots of things. It moves methane and other pollution from the air. People can't cope with that. But they're coming round to the idea that these natural processes. I said to Franz the other day, the sun warms the earth and it grows plants. It does more than one thing.
A little bit more.
This is how natural processes are. So yes, if the funding is there, then we'll run as fast as we can. It's
Okay,
kind of
now
what
the
we've been
question
doing
is
with what we've got so far.
Let's talk about your funding, because you say you have a partner. Hooray for you! That's good news, because
Yes,
I don't think the marine cloud brightening idea is even close to having a partner yet. What I'm thinking, and this is maybe pie in the sky, is that we suppose we could combine not only your two projects, the marine cloud brightening and the aerosol business, but there are other operations that might work. One is cirrus cloud thinning, and we have yet to talk to some people who have experimented with that or studied a little bit. I think it's not very far advanced, and I think that the people promoting it are not particularly confident that it will be successful. But we ought to look at it. But let's imagine that we have 3 different projects that could all do something in Hudson Bay. Now, I believe the cirrus cloud thing could be done in the winter. In fact, it would need to be done in the winter. So there wouldn't be any contradiction between your projects and that. But what I was thinking, suppose we all work out the details of what it would look like and what it would cost. And then let's go to talk to Environment Canada and let's see whether or not we can convince them that this kind of experiment in Hudson Bay would be a huge contribution and that the government ought to fund it. And we should probably find some Canadians. I think we'd better find some partners in Canada who are interested in this, because Canada is not going to want to invest money unless we have some people here who are academics or other scientists, maybe people in government, I don't know. Anyway, let's think in terms of actual planning, what it would take to make something like this work. Your guess, how long are you going to take to do this thing? Because I think Stephen's project is going to take, well, you can see some results the first year, but I don't think it is going to be conclusive until the thing is run several years. Do you, Stephen?
No, we get a result from about a week's for images. We can put them together and average them, and we'd see the result. So I think if I wasn't doing anything about the sea vessels, just doing spraying from a land site and not bothering at all about how the energy is generated to do it, we could get something done in 2 years. That would just be a land-based.
Wait a minute, you don't have the nozzles yet, do you?
No, but that would I could make the nozzles and put them into an ISO container in 2 years.
Okay.
Yeah, that would have the filtration to get the water very, very clean and make the spray. And I'd get energy from something like a wind turbine. It'd have to be a clean energy source, but you can get little wind turbines very easily now. They would be fine. I'm sure the winds are good in Hudson's Bay. And so I could have the land-based source in 2 years' time if there was enough money to do it.
But now you're going to want to run this. I don't want to contradict you. You're the man. But the problem is people are saying you got to watch out for all the dangers that might affect. So one of the things is the possibility that there'll be side effects. Primarily, I guess the worst prediction is that there would be floods in Africa and Pakistan because of the water that's being injected to the clouds that might fall where we don't want it to fall and in amounts that we don't want. So you're going to have to run this thing for a period of time. 1 week is not going to be enough to tell you whether or not you're going to have negative side effects, right? So
the amount that we'd be doing in Hudson's Bay would not have any effect at all in Pakistan. It's a long way away.
You're pretty sure of that. You don't have to worry about it.
No.
Okay. So you're saying that one little experiment and within a week you get your results and we can all go home?
No, I would like more than 1 week, but within 1 week you get your first result, and then you repeat it, and then you get more confident in it.
Yeah.
But I need to get about 100 images from a satellite, and then the image changes in the time it takes for a cloud to move one cloud dimension. Okay, so
now,
you get probably you get 20 or 30 images a day, and I'd like to get 100, but some of them will be in the wrong wind direction. So that's why I say it would take about a week to get enough enhancement of these very faint results that you could convince someone.
Okay, you can convince people that you're brightening the clouds, but
Yeah.
how are you going to convince people that you've actually changed the temperature of the water? You have to measure the water, don't you?
You will have that, because the extra energy that's being reflected up from the clouds didn't get into the water, so you know how much
Now
you
we
were
want
cooled.
to. Ideally, we want to be able to freeze the water. Question is, I don't think you know how much it's going to cool the water, do you?
Yes,
Do
I
you?
think. Yes, I want to cool it by about 4 degrees.
Do you know that we will?
But this
I mean,
this would happen if I had more than one set of sprays going. I'd want a few hundred of them.
Uh-huh.
I'd be able to detect the result from one spray unit.
Okay, now our experiment now. It's mine now too. You got to let me in on this. We've got these 4 stations along the shore, and they're spraying, but you actually need to know whether this thing is going to actually cool a little bit of Hudson Bay, a significant amount of Hudson Bay. You're going to have 100 spray nozzles going, and for a period of time. Is that right?
Yeah.
Okay.
But you'd know the answer that you want from a small unit spraying and having its cloud images treated and processed. You'd see that really is I can, if you let me take over the screen, I can show you what it would look like. I got a computer model of it. I'll run you through this. This is a satellite image of South America. Okay. And there's clouds all over. All right. And what I'm doing is I'm going to be releasing some spray from 4 different places here. All those that's already happening in the reality. I'm going to modify this with the computer additions, and what I'm doing is I'm going to be putting on the amount of brightness change that I get from a number of assumptions here, which are fairly average, and this is going to be changing the CCN concentrations in 4 places along the photograph, with narrow or medium or rather wide spray divergences. Okay. And if I didn't have any clouds, the wakes would be looking like this. All right. This is a very narrow spread, and this is getting wider, and there'll be another one over there. Right. Yeah. So that's what the mathematics has been doing to this image. And that's showing you with a bit more contrast, so you can see it. Okay, so that's going into the computer. And I'm now going to be changing according to the Toomey effect, which is this bit of algebra here. And this is what it does to the clouds. And it takes a bit of convincing someone to pay me money for this result. It's very disappointing. The brightest, the narrowest one is under this V here. And sorry, it's not going to work. But if I take 100 of those, okay, this is what's going to be happening to the brightness of the pixels, and you can't see much difference, but you can if you look at the difference between the reds and the blues, and that's what we've done to the different places across the width of the satellite. And when I bring that up and I take 100 of them all together, this is going back to the image of South America. And you can see the brightnesses here. You probably can't see that one. If I do a little bit more aggressive spraying, I can get other ones like this. And this is now less miserable. This is putting in a bit more spray coming in and a longer lifetime and that kind of stuff. And we're getting a result like that from the 4 different wake angles. Okay, so that's the experiment. This is enough to convince someone who understands the
Okay, now
science.
here,
it's
Stephen,
working.
let's pretend you've got an appointment with Justin Trudeau, and you take this thing and you show it to him. Now
Yeah.
you convince him showing that picture. Tell
Yeah.
him tell me what you would say to him, and why that particular photo should be so impressive.
Well, we're proving that we are changing the brightness of the clouds, and if we know
How
that this
so?
is it,
Explain. See, I don't understand that. You
right,
need
but we
to
can't.
explain
If,
how
if you
those
just
three little images prove anything. What am I to infer from looking at those?
what the images are doing are adding together lots of different cloud images, and that means that the very small change that you couldn't see before, you can see if you average it over a large number.
Now, if we go from left to right, each of these sprays is progressively what? More what?
Well, they're different widths. I don't know what the spray width will be, how far it diverges. So I did 4 of them, and that's the narrowest that it's likely to be. And this is a wide one.
Is this
That will depend on the local turbulence. You can see any of them.
Is it the same amount of spray that's coming out of all
Yes.
4 nozzles?
That's right. Okay.
Oh.
And the spray comes out and it gives you a sort of bell-shaped concentration. And these are different widths of bells. And we can see any of them. It doesn't matter how much width we get. We can still detect the 4 of them.
Well,
Even though this is a tiny
side by side of before the spray and after the spray. If we would do much better looking at the both of them together, then we could really see that the effect was bigger.
I'm not sure if I've got them on this image, but I could find another place where you can see them side by side.
You
But
don't have to do that for us. You just maybe have to do that. Well, for whoever needs to know about this project, if it is worthwhile or not.
Well, let's go back, and that's what I would show them. And I've got 100 of those. All the clouds are different positions. There's 100 different ones, and you can see the result of a ship that's already there releasing material. There's probably 3 ships, but they're producing a lot more than we would be doing from our spray vessels.
Sorry, is that what we're seeing? Some ships down there are spraying something?
Yeah, around here.
All right.
Yeah, and then
That's a sulfur acid droplets.
these are ordinary clouds. Yeah.
Okay, now I want to think in terms of what we've got to convince the people in Ottawa to do, and we've got to tell them that at the end of a period of a year or 2 or 3 years, how long you're going to say, you're going to actually show that you've been able to cool a certain amount of the water by a certain amount of degrees, and this is going to be if both of these projects take place simultaneously or could be combined operationally in a large scale, say covering all of Hudson Bay, then you could refreeze all of Hudson Bay. And you want to be able to show that. That's right.
I'm not to do the sums about freezing all of it, but certainly I've got the sums for freezing the whole of the Arctic Ocean and how many vessels we need for that.
Okay.
And I think it will be similar. I think we should be able to do that with perhaps 100 vessels. We might be able to save a lot of the ice in Hudson's Bay.
Okay. Now listen, Franz, can you see going to see Justin Trudeau and making a pitch that's going to be consistent with what we've just seen? How soon could we get something going with your project, and how much money is it going to take at a wild guess? And how long will it take to complete the thing?
Okay, we will discuss it in our group.
Okay.
Yeah. I mean, we just have to make something up now.
Yes.
we have been talking with other people as well, including a Canadian person.
Well, Well, if
Yeah.
it'll work in Hudson Bay, you can be very confident that it'll work in other places too.
That's what I mean.
Yeah.
That's why you need to do the project. Otherwise, I see not enough reason to put all that money into the project unless it's used to show you could do it elsewhere.
Absolutely.
Okay, my impression is that to be convincing, you're going to have to actually refreeze at least 1 square mile of Hudson Bay and say, you see, we did it, we can do it, we could do it on a bigger scale if you let us. But now I'm not sure that you can do it with marine cloud brightening alone. I don't think you know that yet. But the two things together might do it, but you're not going to have them working together. You're going to have them experimenting in different places so you don't confound each other's results. So you want to be able to show at least 1 square mile where you've actually combined forces and produced some ice that you can then use.
No, you just have to show, you really just have to show the change in cloud brightness.
No, I don't think that'll convince people in Ottawa.
It'd be nice to, as a publicity stunt, to freeze some ice. That would be nice. And it'd be if there's some money to enable that to happen somehow, then that's great.
To sell this thing, you need to show that it's actually going to have some benefit. Even the experiment is going to be beneficial.
We
somebody.
definitely do. I agree.
Right.
We need to. It needs to, on a scientific level, it needs to have certain goals that it can demonstrate. It then needs to demonstrate those things. This is how much methane
Right.
got depleted.
agree.
And this is how much cooling.
That you
Well, we could
research-
put thermometers into the sea and we could show the reduction in sea surface temperature by a lot of thermometers, but that's a lot more expensive to do than to look at a photograph of a satellite, which is
I want to make a different pitch, which is that there are people living there, and those indigenous people are having a hard life. And if you can say we can do one little thing to create a job for these people, or to create ice so that they can actually go out there and catch some seals, then that is a doubling impact on the argument for funding this thing in Ottawa. If you can't say we can do anything that's of any value to real people living there with this experiment, then I don't think it's not going to catch fire or get any support. That's my guess, that you need to show that the indigenous people there would like to have you do this because it actually could help their livelihood. So let's figure out how to.
It'll be a lot more expensive to be able to really produce increased ice that you can there will be no arguments about that. That's you're having to build a whole fleet of boats to do. But what I'm trying to do is to find the cheapest possible way that will convince people that it will work.
Yeah.
I don't think it's going to convince them unless you can show that the Indian people want it.
Would there be some scientists among those indigenous people that would understand?
Research. We have a guy named Lawrence Martin who's conducting some sort of research, but I don't. Yeah, it'd be great if we could find some Canadian scientists who also want to be part of this. Do you happen to know any?
Do we? Yes, there's Paul Beckwith. We know Paul Beckwith.
Yeah, I don't think he's in a position to do the research.
No.
He kind of,
We can certainly do some asking.
there must be people in government who are responsible for things like that.
Must be so many.
Yeah. So
Yeah.
look it up. And Peter Wadhams may know anyway, because Peter has contacts.
I think
Adele?
you're stretching it far too much to say we need to make more ice for the indigenous people. That's just out of the question. The other topics are to prove that it could be cooling. That's a big enough project. It would take a lot to make the ice safe. I mean, you just it's too much.
I don't think that anybody will buy it unless you can show, yeah, we could really make ice.
I think the most important is in the first thing to stop the heating,
Yes. Yeah.
Yeah.
and then we can speak about to begin the cooling.
Mm.
To my
Yeah.
Unfortunately, Lawrence Martin said that the elders, who are the most influential people in the indigenous communities, basically believe that global warming is a natural phenomenon and that nothing can be done about it, and you shouldn't try. So he's not of that mind himself, but he finds it a bit challenging to try to have a conversation with them about it. So they're not looking for ways of trying to change global warming. But if you were able to show them that you could refreeze the ice in a certain area where they live, that would be very, very impressive. And that would make all the difference in the world. So, think about it.
Well, if
two or three or four of a project.
Oh, but that's not necessarily the case, Adele. What we have to do is figure out the temperature of the water and how much you have to cool it in order to get it to stay frozen in the summer. It freezes in the winter. We just have to keep it cooler, enough to stay all summer. That's the name of the game.
I'll show you one more screen share. I've got everything on one page.
All right.
All right. So I'm going to go back to screen share, the green button.
Yeah.
Right.
look,
That's
Mr. President.
That's our mathematical spray patterns. Here is what happens from one image. Okay. And this is the result that you get. And this is what happens if you put 100 images together. And we know how much sun was going in to the top of the clouds here. And we can say, we definitely know that this bit here is getting more sun than this bit here by this amount. So underneath that line here, it's going to be colder than it is here.
Yeah.
All right.
Question is anybody going to be impressed by that?
I wrote a paper about this, and I sent it into Environmental Research Letters, which is one of the most prestigious journals for this, and they rejected it. They wouldn't publish it.
Why did they say why? Why not?
I think they completely didn't understand the point. They thought I was trying to do a computer model.
Well, you have to be able to explain it clearly and convincingly. And this is frankly not convincing to me, and I don't think it'd be convincing to Justin Trudeau if he's the guy we've got to convince. So we got to think of a way to actually get some ice on the water.
Yeah. I think what Stephen is saying is you don't need to change the brightness of the cloud very much over the whole, over the amount of clouds that you're changing around the world to have the desired effect. It just doesn't look very different. It just doesn't look very different. And the problem is, how can you tell that it's worked? And so what Stephen is saying, that here's a technique he's using, sort of a photo enhancing technique, to see that there is indeed an effect. The spraying did actually have the desired effect.
Look, I want this project to be accepted in Ottawa. I don't think it's going to be. I don't think they'll buy it. I wish they would, but I don't think they will. I don't even think Douglas will support it.
Do you mean the marine cloud brightening, or the iron salt aerosol, or both? Or the titanium one?
Them.
The titanium one.
I would like to combine them. I don't think either one of them right now would be enough to get millions of dollars and a go ahead and do it.
But Meta, I think if we can see that the temperature is going down, that's the effect we want to see. To see the sea frozen is much more than can be
done.
But it's very expensive to put out hundreds of thermometers in the sea.
Yeah.
That's a major experiment. I mean, there are things that are floating around the sea now taking temperatures. We can look up what it costs, but they have buoys that are floating randomly, and every so often they plunge down and measure temperatures and salinities and everything down in different depths. And I think they're called ARCO floats.
When we talk about the problem in the Arctic, it's all about how the sea ice is melting, and that's the conversation. The ice, when is the ice going to be gone? We know that the black water is, when the water When the ice
Yeah.
is gone, the darkness is going to exacerbate the problem. It's going to be like a tipping point, etc. So the whole name of the game is to keep as much ice as possible in the Arctic. And unless you can show that you can make some ice, I don't think anybody's going to be interested in your
Yeah,
space.
but we can show we can reduce the temperature.
But
And I
that's
think
not going to
everybody
convince
believes if
anybody.
you can reduce the temperature, you can make
It wouldn't convince me. Unless you can show me that you can do something to maintain the ice, real ice, white ice that reflects light, then I'm not going to want to invest in your project. I don't think I can get Pugwash to buy it.
Well, we're done then. We have to forget it.
Yeah, it's for scientists. This is for scientists to take an interest in.
Just reducing the temperature is, which would be extremely difficult anyway. Never mind the ice. Just reduce the temperature, and then such a technology could be deployed globally if we desperate enough to need global engineering everywhere, geoengineering. So that's why it would be reasonable to say, Canada, you have to step up in the global geopolitical world, do something useful to help the world. And this is one, if you could show to just reduce the temperature, then it could be deployed in a wider place. And that would be my only reason for supporting it. And I think maybe private investment from some of the concerned billionaires like the Microsoft people or somebody might take an interest in such an experiment.
Okay. I mean, I hope I'm wrong, but let's see what we do. This is almost our final conversation about this subject, because there may be one more show. I'll probably put on one about cirrus cloud brightening, which I don't think is a very promising thing. But if we don't have a convincing pitch,
Difference between getting 30 million to do it, to prove that it works, and 300 million to actually do it. 300 million, I could produce a lot more ice. But the chances of getting 300 million
let's look at it
without
this way.
having the proof,
maybe Hudson Bay is just too big. You can't do it on Hudson Bay. Find a small lake that you can actually do it on. I want
we
some
could
ice.
we could do a small inlet in Hudson Bay.
How about James Bay?
Okay,
But
yeah.
the
We do
problem
anyway.
is,
James Bay.
The smaller bit you do, the better chance you have of being able to get the result.
Okay. And can we take a bay off of, or a little
Yeah.
corner of James Bay and
Yeah.
say, let's freeze some ice there?
Yeah, and but that and then that'll cost maybe 100 million. The 800 million does the whole world. All right.
No.
I think-
For our experiment, instead of trying to cool a part of Hudson Bay, let's take a part of James Bay and cool that, because
Yeah.
it's smaller and maybe we can actually get some ice.
Yes, there's a good chance you might be able to do a small bit, and that won't add a great deal more scientific value than the cloud change.
I mean, to your
You'd have to
mind,
be-
but if you can show some ice, I think that's going to be persuasive.
Well, with
1 square mile of ice is all it'll
Okay,
take. If you can show you
with
can
more
make it,
with
that's
more
going to be
spray
convincing.
sources, you'll be able to produce some proper ice, but it'll be a lot more expensive and slower.
why?
But you'll be able to do it. You know,
If instead of Hudson Bay with 4 stations, let's put our 4 stations on James Bay, which is smaller, and maybe we can maybe we can make some ice. Why would it cost more to do it there than in Hudson Bay?
Well, do you think you can stop the wind blowing over? Because if you've got air that's been warmed a few miles away, 20 or 30 miles away, and it's been warmed by the fact that there wasn't so much cloud there, and it warms over the part of the ice that you're trying to melt, then your whole experiment is ruined. So you need to erect an enormous wall all around this piece of ice, this square mile of ice, to make sure that no warm air can blow in there. It's not the way it works. It's an impossible. It's not a real experiment. It's just a demonstration.
If you made a little ice you would then have to prove that this ice wouldn't have occurred naturally.
Yeah.
Because otherwise, people would and others would just say, "Well, maybe that ice would have formed anyway."
Well, that's where your mathematics and his little pictures with 100 composite photos would work. I mean, he can make his case, he can argue, but unless he shows the ice, I don't think anybody's going to buy it.
Let's see what people say when they see this. Let's see what response we get. Let's see.
Okay. Time's up and then some. We've done an hour and a half.
Yeah.
Okay, guys. Thank you. And I'll be back in touch.
Thank you for having us.
Bye.
Bye all.